standard. These questions focus on molecular orbital theory, VSEPR, and coordination environments, which are heavily targeted in the exam. Question 1. Molecular orbital theory and heteronuclear diatomics. Question. Draw the molecular orbital, MO, diagram for the County molecule. B. Explain why County acts as a strong pi acceptor ligand despite carbon having a formal negative charge in its major resonance structure, and account for the HOMO-LUMO gap. Solution. Mo energy level diagram for CO. Carbon, 2 squared 2p squared, and oxygen, 2 squared 2p 4, exhibit significant sp mixing. Because oxygen is more electronegative, its atomic orbitals, AOs, lie lower in energy than the corresponding AOs of carbon. The electronic configuration of CO, 14 electrons, is. Key distinction, non-crossing versus crossing. Due to strong sp mixing, the sigma_2's orbital, often labeled 3 sigma, gains significant 2p_z character and becomes higher in energy than the pi_2p orbitals. It acts as the highest occupied molecular orbital, HOMO, with its electron density heavily polarized toward the carbon atom. B. Pi acceptorability and protonation. Pi backbonding. The HOMO, 3 sigma, is localized mainly on carbon. When County coordinates to a transition metal, it donates this lone pair. Crucially, the lowest unoccupied molecular orbitals, LUMOs, are the pi_2p antibonding orbitals. Because carbon's AOs are closer in energy to these pi orbitals than oxygen's, the pi_LUMO lobes are spatially much larger on the carbon atom. This allows transition metal d orbitals to efficiently overlap and backdonate electron density into CO's pi orbitals. Protonation to HCO +. When a proton, H +, attacks Colorado, it binds to the lone pair on carbon, the HOMO. This positive charge drastically lowers the potential energy of all molecular orbitals. Because it stabilizes the bonding and non-bonding pairs, the energy gap between the new HOMO and the LUMO increases, making the molecule less prone to further electrophilic attack. Question 2. VSEPR versus Bent's rule and energetics. Question. Predict the geometry, hybridization, and exact positions of fluorine and methyl substituents in the following molecules using VSEPR theory and Bent's rule. PCl_3F_2. B. CH_3_2PF_3. Solution. Structure of PCl_3F_2. Steric number calculation, for central atom phosphorus, P, group 15, 5 valence electrons. Geometry, sp3d hybridized, trigonal bipyramidal, TBP. Substituent placement, Bent's rule. Bent's rule states that more electronegative substituents prefer orbitals with less s character, axial positions in TBP, which are PD hybrids, while more electropositive groups prefer orbitals with more s character, equatorial positions, which are sp² hybrids. Therefore, the two highly electronegative F atoms occupy the axial positions. The 3 Cl atoms occupy the equatorial positions. Result: the molecule possesses D_3H symmetry with an axial FPF bond angle of 180 circ and equatorial CL-PCl angles of 120 circ. B. Structure of CH_3, 2PF_3. Steric number, same configuration, 5 bonds, sp3d-TBP geometry. Substituent placement, fluorine, F, is highly electronegative, right arrow prefers axial sites. Methyl, CH_3, is electropositive relative to F, right arrow prefers equatorial sites. Since there are 3 fluorines and 2 methyl groups, 2 fluorine atoms go to the axial positions. The remaining 1 fluorine atom and both CH_3 groups occupy the equatorial plane. Angle distortion. Because the CH_3 groups are bulky and electropositive, they push the equatorial PF bond away. The equatorial CPC angle opens up to greater than 120 circ, while the axial FPF linear bond bends slightly away from the methyl groups. Question 3. Latin